Okay, here's lesson 4-5, complex numbers, and we're going to call this video lesson The Ayes Have It. Actually, we're going to have to divide this lesson into two parts, so we'll see how this goes on for the first 15 minutes or so, and then it's just too long a lesson. We're going to have to divide it into two parts in order to get it up on YouTube. So there'll be a 4.5a and a 4.5b. By the end of this lesson, and both lessons and all, you'll want to be able to find solutions to polynomial equations. Well, I know you've solved polynomial equations before. Here's a quadratic equation, and this is the issue we're up against with this lesson. If you want to solve this thinking about real numbers, then you would take a look at the equation, maybe think formula. I'm going to bring up this and try to say, okay, if I was going to solve this one, I'd say, well, before I even solve it, let's look at what the discriminant would be. That's, remember, b squared minus 4ac. That's the part of the quadratic formula under the radical sign. And recall that if that value is negative, then there are no real solutions. Okay, so in this case, b is negative 4, and a is 1, and c is 6. So b squared minus 4ac would be 16 minus 4 times 1 times 6. Well, that would be 16 minus 24, which is equal to negative 8. Now, of course, that number is negative, so what that means is since b squared minus 4ac is negative, there are no solutions. That's what we're comfortable saying, but of course now we say a little bit more descriptive, there are no real number solutions. So this happens a lot in mathematics. We'd like to have all equations have solutions. So we're going to expand our number set so that there will be solutions. So we're going to actually expand it so that we're going to contain now complex numbers. So the complex number system is kind of built in the following way. We want it to contain all the real numbers we're already familiar with. We want all the operations that held before to hold again in all the rules. So we want the commutative property, the associative property, all our operations in arithmetic, addition, subtraction, multiplication, and division to work the same way with these complex numbers. We're going to actually solve the problem of having no solutions to certain equations by defining the number I, the imaginary unit, to be such that I squared is equal to negative 1. So imagine that. Right? You're going to square this number and get a negative 1. So it's the square root of negative 1. We're going to express our complex numbers in standard form by writing numbers like a plus bi. So this is how these numbers are written. They're not using just singular digits. They're written like this. And we define what it takes for complex numbers to be equal in the following way. Two complex numbers, a plus bi and c plus di, are equal if and only if a has to equal c and b has to equal d, which means the numbers have to look exactly the same in order for them to be equal, which makes sense. So let's consider 6 plus 2i as a complex number. We call 6 the real part, and we call the 2i the imaginary part. So it kind of takes two parts together to make a complex number. If in some cases we don't have a real part, then we would just have something like 2.5i. We refer to these complex numbers. These are still complex numbers because 0 plus 2.5i is a complex number, but when the real part is 0, we say we have an imaginary number. Well, if we take a look at these properties of the complex number system and focus on the fifth one, what it takes for two complex numbers to be equal, we'll tackle this example. What would x and y have to be if negative 4x plus 5i would equal 8 minus 6yi? Recall that in order for real numbers to be equal to each other, the real part has to be equal to the other real part, and the imaginary parts have to be equal also. So what we're going to do is write one equation. We say that negative 4x equals 8, because those are the two real parts. Solving for x would equal 8 divided by negative 4, which is negative 2. And that's what x would be. Remember, we're finding x and y. As far as y is concerned, the coefficient of the imaginary unit I from the left side, 5, has to equal that coefficient shown in the imaginary number on the right side. So 5 equals negative 6y. So if we divide both sides by negative 6, 5, 6, negative 5, 6 is equal to y, which we can express just like that. So there you have it. We found both x and y in that situation. So let's just move this one. Now let's focus on 2 and 3. Just about all the arithmetic rules hold, and you're going to see there will be one arithmetic rule that works with real numbers that doesn't work with imaginary numbers by the way that we build the complex numbers set. So we're going to have to, we'll talk about that in a little bit, but the other thing is that this number I, which is kind of strange. Well, we're going to perform some operations with complex numbers, and you'll find that as we do these examples, we're going to treat the real and the imaginary part as if they are representing real numbers, because again, all our operations and arithmetic rules hold with the complex numbers. So if I could bring this up again here, and let's clean it up. Let's consider adding two complex numbers, 2 minus 3i and 1 plus I. Those are two complex numbers. So if we added those, we would write 2 minus 3i, and I'm just going to write the other one without the parentheses. And we're going to just associate the real parts together, that would be 3, and associate the imaginary parts together, and that's negative 2i. So the sum of those two for part A would be 3 minus 2i. Part B, another example, subtraction. Well, again, if we're going to follow the same rules with real numbers, we'd write this as 2 plus 3i, and then we'd say, well, that minus is going to kind of be distributed over the 4 minus 2i, so it's minus 4 plus 2i. And now it becomes kind of like example A, right? We combine the imaginary parts, the real parts, excuse me, that's negative 2, and now the imaginary parts plus 5i. And I'm purposefully writing these in the form A plus bi. So that's negative 2 plus 5i. For part C, multiplication. What we have here is an imaginary number, 10i, that's being multiplied by the complex number 5 plus a fifth I. We'll distribute, and that would give us 50i. And then 10i times 1/5 I, well, the 10 and the 1/5 would multiply to give us a product of 2, and the i's would multiply to give us 2i squared. So we write this as 50i plus 2 times, and I squared is equal to negative 1. So it's 2 times negative 1. I'll write the real number part first. That's negative 2 plus 50i. And there is our product of those two numbers. And lastly, D. We'll do D right up here, I guess, give ourselves more room. In D, we're kind of multiplying two complex numbers, and it looks to us like we're going to use FOIL, and that's exactly what we do, because we're going to have to multiply the real part, distribute that, and distribute the imaginary part, each one. So we'll do FOIL, and we do our first terms as 6. Our first factors is 6. Our outers would be minus 15i, inners plus 2i, and the last would be negative 5i squared. So let's clean up a little bit. 6 minus 13i, because that's what I get when we add negative 15i to I. And then this minus 5i squared, you start to see what happens with this. When you have negative 5 times negative 1, what I guess happens is we get 6 minus 13i, and the sign changes, right? So if we want to deal with I squared, it's kind of the coefficient of I squared with the sign change. So combining the 6 and the 5 would give us 11 minus 13i, and that's our product. That's kind of interesting. It's 11 minus 13i. So as you can see, these behave very similarly to when you're dealing with real numbers and you've got a variable that's taking the place of a real number. Let's clean this up. We got a few other examples to look at. We're going to look at some special products here now. Again, 4 plus 5i, 4 minus 5i. I'm hoping if you looked at that, you'd say, well, those are the same two terms, sum and difference. So when you multiply those together, it's a difference of two squares. If you didn't recognize that, like I just said, then hopefully you do now as that reminder. So on part A, we don't really have to do the FOIL. We can just say, okay, let's square the 4, that's 16. And let's square the 5i, would be 25i squared, and it's a difference. Again, I squared is -1, so negative 25 times -1 is positive 25. Or as you start to become a little bit more expert at this, you'd say, well, since that's I squared and that's -1, -1 times -25 is plus 25. And 16 and 25 is equal to 41. B is a binomial that's squared, so we're going to recognize that a binomial squared is a trinomial. So remember, that's 3 terms. Trinomial is 3 terms. We square the first, is 9. We double the product of 3 and I, that would be plus 6i. And we square the second term, plus I squared. Of course, that right there is -1, so I'm just going to write that now. 9 minus 1 plus 6i. And 9 minus 1 plus 6i would be 8 plus 6i. And that's our special product. Okay, you can stop this if you don't want me to clear this right now and take a look at these again. I think we'll end this part of the lesson with looking at our powers of I. And an interesting thing happens with our powers of I. Normally, as we increase the powers of other variables, we get different answers. But what happens here is really kind of interesting. Let me bring this up. We'll go through the powers of I. So we're going to begin with I to the first. Let's try that again. I to the first is equal to I. I squared is -1, kind of by definition. I cubed is equal to I squared times I. Well, squared is equal to -1 times I, which would be the opposite of I, or some people say -I. And then I to the fourth, we know from our rules of exponents that the fourth is I squared times I squared, and I squared is -1. So if we square -1, we get 1. So if we look back in these 4, I to the first is I to the second is -1, I to the third is opposite of I, or -I, and I to the fourth is 1. These are the only 4 we have to remember, because what happens when we go to I to the fifth, I to the fifth is equal to I to the fourth times I, and I to the fourth is 1. I is I. 1 times I, identity, that's I, right? And I to the sixth, I to the sixth would be I squared times I to the fourth, and I to the fourth is 1 again, so I squared is -1 times 1 is -1. And you can see we're starting to repeat these values. So if we went out there a little ways and said, well, what's I to the 33rd? Well, we could go continue building up this, recursively keep building this up and find I to the 33rd by finding I to the 32nd first, but we'll need I to the 31st before that, and I to the 30th. But if I to the 33rd, we could write as I to the 32nd times I. Well, I to the 32nd, I think we can conjecture, is the same as I to the fourth, because 32 is a multiple of 4. So I to the 32nd is 1. So I to the 33rd is 1 times I, which is just I. So anytime you consider a exponent, a power of I, it's going to be one of these 4 values. So we'll stop it there, and we'll continue on with this and see how we can continue to deal with operations with complex numbers and use them to solve equations.